Suppose we have a velocity field like so. So this is kind of rotating, but it's also, so this is maybe describing the position of some fluid. So it's rotating, but it's also kind of spiraling outwards. Okay, so, and then, fill this in with other such vectors. So in this context, we might be interested in, so now draw some curve around here. We might be interested in how fast, or how much, I should say, how much is flowing out of this region. So first, let me introduce some terminology. So a curve is simple if it never intersects itself, if it does not intersect itself and is closed or is a loop if it starts and ends at the same point. So symbolically, this is saying R, it's simple if R of T1 equals R of T2 implies T1 equals T2, and it's closed if R of A is R of B. Again, this is so C is a curve parameterized by this. And this, we've stated the definition in terms of this R, but different parameterizations will give the same concept. So, I guess simple and not simple, and then closed, and that is not a line, closed and not closed. So here would be an example of a simple closed curve. Here is a closed curve which is not simple. Here is something which is simple but not closed, and here is something which is not simple and also not closed. Okay, so and so we're interested mainly in simple closed curves because we wanted to talk about regions, which are sort of two-dimensional shapes, but we'll talk about these by their boundary curves. So for simple closed curves, we can talk about the region enclosed by C without running into complications. Okay, so if C is a simple closed curve enclosing a region R, and F is a vector field, then the flux of F over C, or we might also just say over R. So this is, right, so if this is like our curve C, previously so let's say that C has these tangent vectors, and then we had like a force field or a velocity field, whatever, in here. Previously, when we were doing the work integral, we were calculating the component of, so this will extract the component of f not along the tangent vectors of the curve, but along the normal direction of C. So the normal direction is what's always orthogonal to the tangent vector, and so this is sort of pointing outwards. I should say the outwards pointing normal direction as opposed to the inwards pointing normal direction, which would be like this. And I'll say a little bit, I'll say a little bit in a second about how to interpret this. Okay, so as it, I guess symbolically, our definition will be flux is integral of C, or integral over C of f dot n ds, where now this is the outward pointing unit normal vector. All right, so how do we actually go about calculating this? So the question is, how do we calculate the normal vector for R? So let's write R. Well, here I'm just talking, last one we were talking about in 3 dimensions. Here I'm only going to be considering 2 dimensions. So R of t is x of t I plus y of t j. Then the unit tangent vector is dx over ds I plus dy over dt, or sorry, ds j. So n is supposed to be orthogonal to t. So although we're in 2 dimensions here, we can find, it's a convenient way to find a vector orthogonal to a given vector is to put ourselves embed into 3 dimensions, and then we can take the cross product. So the cross product of t with the unit, cross, not dot, yeah. The cross product of t with the unit vector k will be, it will be orthogonal to t, which is good, which is what we want. And it'll also be orthogonal to k, meaning, which equivalently is saying, this is still even though we moved up to 3 dimensions, the vector that we get out is still going to be in the xy plane. So this is what we will choose for the normal vector. Oh, and I guess I should say, since actually, no, let me just, so this, yeah, I'll say that the normal vector, from this definition, we can see has norm 1 or has magnitude 1. Okay, so this explicitly is, so determinant, sort of fake determinant formula, ijk, dx by ds, dy by ds, 0, 0, 0, 1. So that's dy ds times I, and then minus, so minus dx by ds j. Okay, now the subtlety about the outward pointing normal vector. So for this to point outward, we need to assume that in our parametrization, we're moving counterclockwise. So C must be traversed counterclockwise as t increases. So, for example, let's take this, look at our tangent vector here. So here, this is just, let's say, negative I. So this is telling us to put the y coordinate, the former y coordinate, as the x coordinate. So that's going to be 0. And then take the negative of the x component. So here, our unit normal, assuming this sort of was drawn correctly, this will be j. Whereas if we took it, so we also could have taken k times t in the other direction, and that will produce, remember when we switch the order in a cross product, we get the negative of what we got. So that would give us this vector instead, which is pointing inwards. So, but then that is, like if we were traversing this clockwise, okay, then our tangent vector at this point would be the negative of what it was when we were going counterclockwise. And so then we would get, then our formula would, if we took this, would give the outward pointing one. So let's write that down. If C is traversed clockwise, then we take n equals k times t as opposed to t times k, t cross k. All right, so summarize that was sort of a long discussion. So f let's take f is function m x y I plus n x y j. C is parameterized by this, and we're assuming this is counterclockwise. Not put parentheses and C's next to each other. Okay, then the flux, which is integral over C f dot n ds, this explicitly is m dy, integral of m dy ds minus n dx by ds. And then integrate that with respect to ds. And this is, in the other notation we saw, m integral m dy minus n dx. And sometimes we'll put a little decoration like this. You'll see, and this is to remind us that this circle is to remind us that C is closed. So it's a loop. And sometimes you will even see an extra decoration to indicate counterclockwise, but that's a little, I mean, the textbook uses that, but that's not as common. So this means the same as the integral without that decoration. It's just a reminder.